In this video, we will talk about Coulomb's law. We will give the mathematical definition of Coulomb force between two charges. We will show how to determine the direction of Coulomb force between a system of two charges. We will do a few examples and solve problems to highlight the concepts provided. Let's first recall an important concept. A charge Q in an electric field E would experience a force F given by the product of that charge Q times the electric field E. So if you have, say, a positive charge like that sitting in an electric field heading to the right, then the charge would move to the right in the same direction as the direction of the electric field, because the sign of this charge is positive. It is a positive charge. However, if you have a negative charge sitting in the same electric field which is heading rightward, the force on such a negative charge would be going in an opposite direction to that of the electric field. So the force would be heading leftward in this direction, signifying that this charge will move leftward. As a quick example, what you have is a negative charge with a strength of -2 nanocoulomb sitting in an electric field with a strength of 5 newtons per coulomb heading in a rightward direction. So the force will be heading in a leftward direction because this is a negative charge here that we are dealing with now. And this force can be computed in a following manner. So the force is Q times the electric field. Now Q is the negative charge, so it's -2 times 10 to the power -9. I am converting nanocoulomb to coulomb. The electric field is 5 in the direction of I hat. So you see you get -10 times 10 to the power -9 I hat newtons per coulomb, which is -10 to the power -8 I hat Newton per coulomb. Now let's apply that result to a system of 2-point charges. Let's say you have a charge, a positive charge with a strength capital Q, and you have a negative charge, let's say here, with a strength little q. Now let's assume that the distance, the center to center distance between these two charges is little r. We know this positive capital Q produces an electric field in an outward direction. So let's just, for an example, look at one such field lines, like that. The force on this little q is the charge of that little q in coulombs times the electric field produced by the capital Q. Let's call it E capital Q. But we know what this is. This is quite simply the constant K times the strength of that charge capital Q over that distance squared, and at that point the direction is I hat. However, since this charge is negative, the force on this little charge is quite simply minus little q, K capital Q over R squared I hat, signifying that this charge here will be pulled towards that positive charge capital Q. So this expression Q, K capital Q over R squared is the magnitude of force that this charge experiences due to the field created by that charge. Now let's reverse the roles. Now let's look at the force that this capital Q experiences due to electric field due to this little q. The electric field that little q produces will be in a direction that is inward towards that little negative charge, and it's going that way. So at this point, the electric field that this charge experiences due to the little q charge would be given by the following expression. It is K little q over distance between them squared in the direction of still I hat, because this electric field is moving rightward. The force that capital Q experiences due to electric field produced by little q is given by that capital Q charge, the strength of that capital Q, times the electric field E, that is this electric field. And putting together we get K little q capital Q over R squared, now in the direction I hat or rightward. So if you note these two expressions, this one and that one, you see they are identical in magnitude. So the force between this pair of charges is given by K, the product of the two charges, over the distance between them squared. Now this is the magnitude of the force between them. This is what we call the Coulomb force, and this expression is known as the Coulomb's law. However, note that although the force on this due to that and the force on this due to that are the same, namely this expression, the directions are different. So on this capital Q, the force due to little q is going like that, and on little q, the force due to capital Q is going like that. Now assume now the two charges are positive, so the force between them is the constant K times the product of the two charges over the distance between them squared. However, the force on the capital Q due to little q will be going in a leftward direction, and the force on little q due to capital Q will be going in that direction. Because as we remember from our earlier discussion, that like charges repel. Let's look at the following simple example. You have two charges. One is positive 2 nanocoulomb, the other one is positive 3 nanocoulomb. They are placed on the x-axis, and the distance between them is 4 meters. So let's compute the force on the 2 nanocoulomb positive charge. Now the magnitude is of course the constant K times the product of the two charges, which is 2 times 10 to the power minus 9 times 3 times 10 to the power minus 9, I'm converting to Coulomb, over the distance squared, so the distance is 4 square of that. Now the force on this 2 nanocoulomb charge due to that charge will be in a leftward direction because they repel, so the direction is minus I hat. Likewise, the force on 3 nanocoulomb due to 2 nanocoulomb is given by the following expression, force on 3. So K is the constant, 9 times 10 to the power 9. The product of the two charges as before is 2 times 10 to the power minus 9 times 3 times 10 to the power minus 9 over distance squared. Now this charge will be having a force in a rightward direction due to the repulsion because of that charge. So you see the magnitudes of these two forces are the same, the only difference is in the direction. Let's look at the following problem. 2-point charges are located at the y-axis as follows. Q1 is positive 3 nanocoulomb at that location, y equals to 0.6 meters, and charge Q2, this one right there, is a negative charge, minus 2 nanocoulomb at the origin. So this is the origin. Find the net force exerted by these two charges on a third charge of 5 nanocoulomb positive charge that is located there. The force on Q3 due to Q1 will be going in that direction. Let's call it F13. And the expression for this force F13 is the constant, which is 9 times 10 to the power 9. The product of the two charges, Q1 being 3 nanocoulomb, so 3 times 10 to the power minus 9. Q3 is 5 nanocoulomb, so that is 5 times 10 to the power minus 9. Over the distance between them is 1, so 1 squared, and it's in a direction of minus j hat. they are like charges, so Q3 will go that way. They repel each other. The next contribution is due to that Q2. Q2 would attract Q3 towards it, so the force due to that is going in that direction. Let's call it F23. So the expression for F23 is the constant 9 times 10 to the power 9. The product of the two charges, Q3 is 5 nanocoulombs, so 5 times 10 to the power of minus 9. Q1, or rather Q2, which is a negative charge, this charge right there, is 2 nanocoulomb. That's the magnitude of it, so 2 times 10 to the power minus 9. And the distance between them, this distance right there, is 0.4 meters, so that's square. Now the direction of F23 is going upward, so it is J hat. To get the net force, all you need to do, the net force on that charge, is quite simply a vector sum of F13 and F23. And if you do that, you get the following answer. 4.28 times 10 to the power minus 7 J hat newtons. So this J hat indicates the net force on Q3 will be heading that direction along the positive y-axis. Problem 2. So you have two equal positive charges, that and that, along the y-axis, and they interact on a third point charge, 6 microcoulomb, sitting on the x-axis, like that. So what is the net force on this capital Q due to the other two charges? Let's contribute one by one. So let's do the effect on the top charge on this capital Q. Now they are both positive charges, so that means this force is going to go like that. It will repel the capital Q in that direction. The magnitude of that charge, let's call it F plus, is given by that K constant. The product of these two charges, which is 3 and 6 microcoulomb, so 3 times 10 to the power minus 6 times 6 times 10 to the power minus 6, divide by the distance, this r here, r squared. Now from Pythagoras' theorem, r is quite simply 0.5 m. Another thing that we need to figure out is this angle alpha, because we need to compute the components of this F plus. So this F plus is going in that direction, so that means it has a positive component, positive x component going that way, and negative y component going that way. Now the second contribution from the lower charge. So this will also repel the capital Q, but in that direction. And the angle here is also alpha, so this force due to this lower charge will again have a positive x component, but the y component now is positive, opposing the negative y component of that charge. The magnitude of the force due to the lower charge, let's call it F minus, is again given by K times the product of this charge and that charge, that's this one here, divided by the distance r squared, which is this. We know what r is, it's 0.5, r squared is 0.25. The y components will cancel each other, so the x components will reinforce each other. So all we have to do is to just calculate the x components and add them up. The x component of the upward force is quite simply the upward force that we have calculated times the cosine of alpha. Likewise, the x component of the downward force is quite simply the magnitude of that downward force that we have calculated there times cosine alpha, where cosine alpha is this distance, which is 0.4, over that distance, which is r, which is 0.5. So note that F plus and F minus are the same. So the net force is this plus that. So 2 times F plus or 2 times F minus times cosine alpha, which we already know, I hat, which will result in 1.04 I hat newtons. And that's the answer. Thanks for watching.